Alright, what's going on, guys? So today we are going to be talking about the affine connection a little bit more, and we're going to be talking about why exactly it's not a tensor. We're also going to dive a little bit into the covariant derivative and geodesics here. I think this is going to be a really good sort of marriage between all three of those topics, and then we'll dive deeper into geodesics and the covariant derivative. If you like this kind of content, make sure to hit that like and subscribe button. Go onto my Patreon page if you want to support the channel, and if you want to get exclusive and or early content, which is not coming out yet for this tensor calculus playlist, because I want a lot of this to be free and open source to a lot of you guys. Anyways, let's get right into the topic. So we're going to be talking today about why the affine connection is not a tensor. Okay, and so first we want to do is we want to define a tensor. Well, in earlier videos we talked about how vectors transformed, how covectors transformed, and they transformed something like this. From, if you recall, vector a mu, suppose we had a prime, transformed as there's a transformation matrix, and here was the old a, say nu, like this, and then we had I'll just write it like this. I'll just put the mu. So this was the transformation of a vector. For a covector, it was at the bottom here, if you recall, right? And then for a tensor, we had a combination of the two, right? So for some tensor mu, gamma, delta, our transformation looked something like this, right? And so we had, say, something that looked like this, because we have, let's see, so these two guys are going to have the index like this with the basis vectors, right? So we have, and then lambda, and then like this, and then so those guys are going to transform, giving the transformation rule for the components like that, right? Because that this is how that guy transforms, and these guys transform like that. Anyways, so we have these things, these transformation matrices, right, that show how these things transform. Notice how there's nothing added to these, right? Nothing added to those guys. And this is going to be important because we're going to see how the affine connection, there is going to be something added here, and so that's what's going to make us say, well, okay, these are not transforming as tensors, therefore they can't be tensors. So let's go into the topic here. So suppose we had some vector, okay, and we want to take its derivative. Its derivative looks like this, okay, and then suppose we want to take the time derivative of that vector. So if we take the time derivative of that vector, we have the derivative looks something like this, okay? And if we sort of follow through with this, the time derivative of this guy right here is going to be through the product rule. And this thing is going to usually be 0, right? Because if we have a transformation that looks like this, right? So the new x nu, if this is what that looks like, when you take the double derivative, so suppose you take the derivative of, say, with respect to x, okay? Well, you're going to then get a cosine of theta. Then you take the derivative with respect to y. Well, there's no y in front of that cosine of theta, so that's just going to go to 0. So in most cases, this guy is going to go to 0. But more generally, coordinate transformations, these coordinate transformations might not be 0. And so therefore, not all the derivatives of vectors are going to be vectors, right? Because this thing is messing with us. We have this additional term that tells us that the derivative of this vector is not necessarily going to be just this part right here. We're going to have this little piece right here sort of messing with us. Okay, so how are we going to remedy this effect? So from the perspective of the vector itself, we're going to say that the acceleration of this vector is not changing, or it doesn't change with respect to a proper time. From the perspective of outside, well, suppose again that the idea here is you have some space-time, and at each point in space you have some vector chi. If you're here, then everything from your perspective is going to look like it's not moving. This was the Einstein equivalence principle, right? The acceleration downwards of an elevator. Well, you're going to feel like nothing's happening to you, so your acceleration is not going to you're not going to feel that acceleration, right? This again, this is the Einstein equivalence principle. This is EEP, right? The Einstein equivalence principle. The idea again is, if you're in free fall in an elevator, right, you're going to be falling in that elevator at the same rate as the elevator is going to be falling. So from your perspective, nothing is going to be changing, okay? But from the perspective of an outsider, you're clearly falling, you're clearly accelerating, and so there is going to be an acceleration there. And so that would be sort of, if we're taking this idea here literally, what we're doing is this first premise right here, is going to be the situation in which you are standing here. This is how you describe that vector. In the other case here, your position vector is a function of some coordinates, and those coordinates can only be perceived by someone standing outside. So someone standing here right here is going to see this vector changing, right? And this vector lives in your space if you're the person right here. So the idea again is Einstein equivalence principle, but with respect to other space-time coordinates, this double derivative might not be zero. So let's see how this works. So here is that double derivative, and we are going to take that time derivative, right? So when we take the time derivative, we're using the product rule again, with respect, since this is a function of space-time coordinates. This is a function of space-time coordinates from the outside perspective. So this is where we're doing the product rule. And then we really just expand this out, right? So when we expand this out, we get this guy right here, okay? And then we can get down to this guy through this stipulation, right? This stipulation here is really just, these two guys are some inverses of each other, right? And the alphas sum over each other, and as long as lambda and mu are the same, then this is going to give us a Kronecker delta. Okay, and so we see here, we now get to this point, and we say, okay, well, we're going to define these guys here as some coefficient, right? Some coefficient. We're going to call it this for right now. We're not totally sure what it is yet, but we're going to see exactly what it is in a few minutes here. So now we get to this point. Okay. So far, so good. This has a special name to it. If we go up here, this is the geodesic equation, right? So we've said that this whole thing was equal to 0. Remember, because this right here, and I believe I'm covering, this is the geodesic equation. The geodesic equation. I'm just zooming up because I think my face is covering some of this. But this right here is the geodesic equation. This it's equal to 0 because we said this was equal to 0, and from this we were able to deduce this. So the picture here again is we have some vector. It's a function of the space-time coordinates. We have some metric. We have a basis. We have we have the bin of real numbers. This is coming from, again, I really like this channel, X, Y, L, Y, X, Y, L, Y, X. I'm drawing a lot of ideas from this channel here, but I'm also bringing in some nuance. I would totally recommend going to that channel and taking a look at his stuff as well. But anyways, this is a picture we have, and now we have these objects. Oops. Now we have these objects here, and these objects are going to be important in the picture here, and we're going to see how they're going to fit in to this picture. So if we take a look at this equation a little bit more, we can see, okay, this is a geodesic equation. This is an acceleration, because it's a double derivative with respect to time. So that means this side must also be some sort of acceleration. So these guys are related to the acceleration of an object in some way. And we're going to see in later videos how exactly they are related. But let's sort of now talk about why exactly these objects are not tensors. So because we have all the tools now to see why this is not a tensor. So we start off with this definition. This is how we defined it. So if we take the derivative, so here we're taking the derivative here, and we're going to transform. We want to transform this guy. Okay, so here is what we have right here. Okay, and so we have, this should be, let's see, this should be a prime, right? That should be a prime because there's a prime right here. So this here, we could see is right here, right? We're just another product rule, okay? Here we're taking this guy out, right? And we're just taking a look at these two guys here, and we're seeing this relationship right here, right? So this is another product rule, okay? So we're not really doing much. We're just doing a bunch of product rules. But we're going to see here, okay, when we're going to see here how this all sort of fits in together. When we take this derivative now, we get here. So this guy here is going to be right here, okay? This here, so this is another product rule for this guy and this guy, right? So we're taking the derivative of this guy using a product rule, and then this guy right here is right here, okay? And then same here, we are taking so here we are taking this guy right here is right here, and then the product rule, this is actually a little bit easier, right? Because we have these two guys right here, and then we're taking the derivative of this with respect to this guy, which is right here. So we have these two terms now, and this term right here. Now we need to multiply everything out, okay? So when we do that, do we have all this? I've just copied it. Oops. So I've just copied it here. So the first term is going to be right here. The second term is going to be right here. Okay, and what we get is we are taking a look now. So we're just rearranging a few things. You could pause the video if you want, but we're going to get this when we do that rearrangement. And then what we could see here, that this guy here, well, that's this. Okay, and this guy here is going to be what this all this equals. So what we get is this. So we have what look to be like transformation matrices, right? We could say that this one, and then there's this one, this looks like an inverse matrix, and then this one here looks like an inverse matrix. So this part here, is what that matrix looks like. And then this here is that added term. So this is showing us that this is indeed not a tensor. And okay, so what's the picture? So the picture we have going on is this right here. So what the picture we have going on is a vector, and that vector is at location of space, P, okay? And what we want to do is we're going to take this vector. We're saying that this is at location P. All right, my apologies. Stupid dog was barking, so I had to go get him. But let's get back to the picture here. So we had this point P at spacetime. And located at point P was this vector here, or with this vector here, we had this whole vector space. This was a metric space. Again, this was a metric space. And because it's a metric space, because it's a metric space, we have this metric here. And once we endowed this with a metric, then we were able to see, well, we have a metric tensor, okay? And then from the metric tensor, we were able to understand that there is a covector space as well. So we can use a metric tensor to take us from our vector to our covector. A covector also has a metric space. Our covector metric space can be, once we realize this is a metric space, then we can understand that we have this metric tensor as well. Okay, and we can convert between these two guys, and we'll see later how that's achieved. It's not something too terribly difficult to understand. And then, so this is all these guys are located at this point in P, right? So, but then we also have this guy. And this guy here, well, this is going to take two vectors. This is going to take a vector at here, and it's going to take two vectors here, right? It's going to take this object. It's going to take this object here, and it's going to take another object that's going to tell us the direction that we're moving, and it's going to take that one of these tensors or one of these vectors, which is located in this space, and it's going to take this vector, and it's going to give us, it's going to spit out a vector that represents, again, what we saw in an earlier video, that change or that notion of parallelism. It's going to give us a vector that tells us what a parallel vector would have been if it would have to have traveled in some direction from P. Right, so that is what that thing gives us. So this thing gives us this vector lives in this space at P. Okay. So we could see this is sort of a messy picture, right? But this is the architecture of spacetime. This is a picture that we're going to build on. We're going to keep on building on this picture, and we're going to understand how this how everything is related to one another, because we're going to find relationships between this guy and these guys as well. Okay. So anyways, this is an alternative way of writing that transformation. Okay, so I'm not going to get too into that. We just use this relationship here, and we could see how we use this to get from this rule we can to here. Okay, I'm not going to get too much into that. You could pause the video to see how that works. But again, I am not going to get too much into that. Let's go back to the original problem, though, because this is what we had. We had come all the way up to this point here where we define these guys. Well, if we say this is equal to this, well, then that means this acceleration vector, this is a vector, and it's representing an acceleration of some object, right? So what we can do is we could say, well, if it's a vector, it has a basis trend. It has a basis. That basis, we can say, are these two guys right here. And so in some way, we're thinking of these guys here as coefficients of some set of basis vectors that define the acceleration of this vector right here. Right, so this is a 4 vector, or this is some vector. It's a function of space and time, and it has these basis vectors, right? Because we were able to recognize that this was a basis vector, this is a basis vector. And so we need coefficients on those basis vectors, and those coefficients are going to be these guys right here. This here is called the second fundamental form. This second fundamental form is going to be the coefficient on this orthogonal basis, and we're going to see a picture on how exactly that this all works. So these again are the coefficients on that basis. This is that second fundamental form. And so these coefficients sit, so that this one's going to be a coefficient for this guy. This guy here is going to be the coefficient on this basis vector. And then this second fundamental form is going to be a coefficient on the tangent, not the tangent, the orthogonal vector that is tangent to the surface or the manifold at this point. Suppose again this was a point P. This second fundamental form is going to be the coefficient on this guy. So we now use this basis realization, which is what I was talking about, to see how this can be construed as a vector. Okay. So the Christoffel symbols give us the tangential components of our acceleration. This should be a... I'm so used to writing R's also when I'm doing work in this area. But anyways, and then this is that second fundamental form. It gives us the normal component of our acceleration vector. Put more compactly, we have this. So you can imagine, say, if you had some manifold that was multi-dimensional, say 10 dimensions. One of those dimensions is going to be reserved for that tangential plane, or for that normal component. All the other components, well, it's going to have that vector is going to look something like 1 mu nu, 2 mu nu, n mu nu, and then at the very last one is going to we're going to have L mu nu. Right, these guys are all going to be components of some basis, and that basis is going to be all of them are going to be components on some basis, with this one down here being a component on that normal component. Okay, we're not going to get too much into this right now though, so I'll just erase this. And so we can, if we multiply both sides by this, we get this, and when we have this, so we can realize that this here gives us the metric tensor, right? Because we have this KL, but KL on the bottom, KL, and then we have these guys here. So we get this, and then we can realize that this, that the inverse of this guy, well, if we multiply both sides again by JML, well, this here is going to be delta, a Kronecker delta, and then from here we can just change the K to an M, and this is a relationship between the metric and the Christoffel symbol. So this is quite interesting, because this is an acceleration, this is what looks to be a velocity, a metric, and the Christoffel symbol. So suppose phi is our position vector. Phi double dot is, actually, I'm not going to get too much into this. This is sort of going off topic. I don't want to have this video go on for too long. But anyways, And the second fundamental form is going to look something like this, right? So this is that second fundamental form. We can do the same thing if we dot product with the tangential part, or the normal component. Sorry, the normal component. Well, the normal component dotted with any one of these, well, that's going to give us 0 because they're all orthogonal. Normal component dotted with the normal component is just 1. So this is what we get for that normal component. So the normal component, both of these have this guy in that equation. It's just that if we want to get the Christoffel symbols, we also have this added GML x, and then this velocity in here. Anyways, this is a long video. We've covered a lot. We've covered why the affine connection is not a tensor, however, and in doing that, we've sort of seen how the affine connection can be thought of also as a set of, the affine connection can be thought of as the components of the acceleration vector, and they sort of work in tandem with the second fundamental form. We've also looked at this picture here. We're going to clean this picture up a little bit in later videos, and we're going to take a look also at how these guys are more related to these guys, because there's going to be a very, very interesting relationship between them that we want to discover. And that was pretty much it. Again, this is a pretty long video, but I think it covers a lot of the basis, a lot of understanding. This is more, gets into a little bit more general relativity, but tensor calculus is really at the crossroads of general relativity and somewhat advanced mathematics, and so there's going to be some overlap between the two topics. But with that being said, again, make sure to hit that like and subscribe button, and make sure to hit up my Patreon page if this is the kind of content you're interested in. But anyways, I will see you guys in the next video.